Good morning, Year 12s. Sorry about that, guys. I've been having major computer issues. It's been doing all kinds of funny stuff, and I was like, I've got to close all my tabs and just flat out restart this. So, yeah, thanks, guys, for being patient. I do apologize. Right, I'm hoping, pause the other video. I popped out the chat. Hopefully you guys can hear me okay. Give me a shout if, just on the chat, tell me you can. That'd be grand. I'm hoping this is all going to work just fine now. So, okay, I'm not going to bother turning my camera off because considering how much problems I've had this morning, I think it's probably just reasonable for me to just be like, do you know what? Yeah. Right, what I want to quickly do, sorry guys, I'm muting my phone. Yay, there we go. Because my phone's developed a new thing. Whenever someone messages me on Google Hangout, it now makes it sound like it's ringing. It's not there. Right, let's crack on, guys. We are doing Hess Cycles Part 2 application. This is going to be a tough lesson, guys. So let's crack on. Okay, share screen. On to that one, winner. I'll hide that bit. Okay, so learning objectives wise, I've put them onto the YouTube video. I need you guys to be able to know when to use a cycle and when not to use a cycle. Obviously, be able to calculate the heat energy change in both methods. And the last one would be to be able to create cycles, because they're going to ask you to do all that. And so what I'm going to do is I'm just going to try and lay out some ground rules. First of all, I've got loads of exam questions that we're going to go through today. I still haven't managed to get my new calculator hasn't arrived off Lazada yet. So I just want to make a couple of notes of when, put a little title of when to use a Hess cycle. When to use a Hess cycle. Because I'm not going to lie, if I can avoid it, nota bene, if you can avoid it, you should. Hess cycles, avoid it, you should. Hess cycles are notoriously tricky, and they're full of points where errors can creep in. And in fact, if you can do it through equations, you're much more likely to have a more reliable answer. That's the right word. So when do we use it? So bullet point number 1, when do you use it? Number 1, when they force you to. When they force you to. I'll show you what I mean by this. So I've got a whole load of exam questions here from Edexcel papers. So question number 1 is forcing you to use a cycle because they are giving you it. Yeah, they are forcing you to use a cycle. And that's fine, because the great thing is they've made it a whole lot easier by providing it. Yeah. So let's look at the next one. Once again, another example where they're forcing you to use a cycle. So here we're having to use a cycle here because they've provided it. In the next one, look at this one, no cycle now. So we've got an option. So this one, we can choose. Yeah, let's choose whether or not we want to do it. This one, right, this one's a great example. This one I would always say try to avoid. So this is the next thing, which is data. Hess cycles are all about data. And what you'll notice is in the questions, what they tend to do is this is considered, okay, let's do data. Okay, so when to use a Hess cycle, number 1, when they force you to. Number 2, data. So there are what I like to do is I like to block the datas into 3 different types. There is, so 3 different types of data. So we've got type number 1 is formation data. The next one is combustion data. Combustion data. And the third is kind of 2. It is either mixed data or, and this is the point I'm trying to make, it doesn't matter if it's mixed data or unlabeled data. Yeah, unlabeled data. So, and what this means is, depending on the data you're provided, kind of helps you choose when and where to use a Hess cycle. If you ever get this one is the really clear one. If you ever have mixed or unlabeled data, do not use a Hess cycle. You will be using equations. I'll just put use equations. It's much, much easier. Yeah, trying to do a Hess cycle with unlabeled data is just mind-bogglingly awful. And I always feel like when students try and do it, they always end up saying, I have no idea whether or not that's correct. And that's not a good place to be in an exam setting. We want to be able to say at the end of that process, I know with absolute certainty that that is the correct answer. These two bits up here, if you've got formation, pure formation data and pure combustion data, you can actually do either, you can do cycle or equations. So you can actually choose at that point because they're actually not too difficult. So I'll show you that in action today. Okay, so let's go immediately to our questions and see if we can start applying this a little bit. So this is a question of 2013's Edexcel Unit 2 paper, and it simply states, it gives you the data. Notice that it's unlabeled. It just says enthalpy change. Yeah, the data is not combustion, it's not formation, it's simply unlabeled. I just want to show you another question. Right, that is labeled data. That there, and you can add this to your notes. Yeah, so what does data look like? Delta HF is formation data. Formation data. Now, what we can now do is let's choose an example. So we've been given in this particular question, it is all formation data, pure data, formation. And what we can now do is we can turn each of these people into an equation. Yeah, because the definition for the enthalpy of formation, the heat energy change when 1 mole of a compound, hi Nish, 1 mole of a compound, 1 mole of compound is formed from its constituent elements in their standard states and under standard conditions. So we can now create, if we're given data, we can turn those into equations if we like. And that's the point of being able to choose now if you want to. Let's do an example. Guys, I'm going to give you a question. So just have a go at this one. Question number 1. I'm going to make that thicker since I can't really read it. Question number 1. Guys, can you write the equation for the delta HF of, what do I want to choose? Water. That's a great one. And by the way, I've deliberately chosen it. I wonder how many people are going to fall for it. So now what you can do, guys, is pause the video, have a go at writing that equation into your notes, and do it in pencil if you like, so that then you can erase. I know that some people don't like scribbling over notes or whatever, so you can erase it then if you like. So have a go at that one. Okay, so the answer is, hey, we know we need to make water, make H2O, yeah, from its elements in their standard states. Water is a liquid, right? Right, the heat energy change when 1 mole of a compound. There is a number 1 in front of that I cannot change. What that means is I've got to halve that guy, and there's my answer. A very, very, very common answer here is for students to double it. You are not allowed to double the equation. No, because the definition states 1 mole of. The heat energy change when 1 mole of a compound is formed. And in this case, it's 2. So this would be delta HF, and this one would be 2 times the delta HF, because I'm making 2 moles of it. So okay with everybody? Nice to mention it. Nice to do a nice easy formation. Cool. Okay, so next. The next type of data, let's go to the next one. Go back to black. Zoom in. So the next type of data, I'm going to make my pen a bit thicker, is delta HC. This, of course, is enthalpy of combustion. Yeah, I'll put enthalpy of combustion. The heat energy change when 1 mole of a compound is completely burnt. It doesn't actually have to be 1 mole of a substance is completely burnt in excess oxygen to form CO2 and water only, all under standard conditions and in standard states. So we can have a go at a question of that as well. So let's do, let's do a question. Question number 2. Write the equation. Write the equation for delta HC of, let's go for ethanol. Why not? Ethanol. Let's see how many of you guys can remember your organic from GCSE. Pause the video, have a go, and then unpause it to check your answer. Answer. So we've got the heat energy change when 1 mole of a compound, 1 in front, I cannot change that 1. 1 mole of a compound is burnt in excess oxygen to form CO2 and water only. By the way, you don't actually have to have both. Yeah, if you have the combustion of carbon, you only form CO2. And if you burn hydrogen, you only get water, but that still applies, it's still okay. So just bear that in mind. Yeah, form CO2 and water, all under standard states and in standard conditions. So ethanol is a liquid, oxygen is a gas, carbon dioxide is a gas, and water is a liquid. Right, so now we can balance this. Let's balance it in green since I did the first one. I cannot change that number. No, don't change. I'm going to put no, I don't like that. Don't change. Yeah, it's in the definition. Right, 2 carbons. 2 carbons. Next, hydrogens, 6. Hydrogen 6. Next, oxygens, 4. 7. 7. There's 1 there, so 3, and I'm done. I like it. And the enthalpy of combustion of ethanol. Love it. Cool. So can we also write ethanol as? Great question. No, that is now dead. I despise Edexcel for that, folks. They should never, ever, 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 ever give you that. I hate it. It's just no way is that ever acceptable. Because that, just to put that on, it's appeared on the chat and I'm now ranting about it. C2H, I understand. I don't know who it, Niyazi, is that you, Shazza? I don't know. Like guys, that is just, it's horrible. It's all kinds of wrong. There are, in organics, there's only so many types of formulae. There is molecular C2H6O. That is the molecular version, molecular formulae, formula for ethanol. Yeah, there is the structural formula, which is this one, a written representation showing the arrangements of the atoms. This is structural. And what they've done is Edexcel, and I don't know why they do it. It drives me mad because I have to then unteach it. Oh, it drives me bonkers. Because what they then do is they take the important part structural and they just whack it into them. What? It's just, it makes me want to vomit. The displayed, by the way. Yeah, we know this. Everyone knows the displayed. Most common mistake is people miss that bond. Watch out, you can't do it. It's the most important bond in the whole molecule. Yeah, there you go. There is also empirical, but the empirical is the same as the molecular because there's only 1 oxygen. Yeah, this is the displayed formula. Displayed form. I'm just going to put form. It's easier. There we go. Thanks, Shazza. Shazza, I'm so glad you asked because no, it's a horrible, horrible thing. Just flat out delete it. That's what I want you to learn from now on. That and that. Yeah, that's what I need. That's what I need. Cool. Right. Okay. So now that we've kind of discussed the data, I want to discuss the cycles for formation and combustion because that's quite a nice thing to do. So let's now can we do formation cycle? Formation cycle. So if you're given an equation, such as let's take ethane. Let's take ethane and let's take ethene. Let's take ethene, react it with steam. It's always nice to do that. Ethene and steam, and I'm going to make, it's actually reversible. I shouldn't really have chosen that reaction. It's done now. Doesn't matter. Doesn't matter. And we're going to make ethanol. I'm trying to reinforce the ethanol, if you're wondering. Yeah, if they now say a formations, if they give us formation data, yeah, they give us a little block, yeah, a little block of formation delta HF data, and they give you the people, you know, ethene, water, yeah, and ethanol. That doesn't help, does it? Ethene, water, and ethanol. What is going on with me today? There you go, water and ethanol, and they give us our numbers. I don't know, formation of ethene, I don't know, plus 600. I don't know, minus formation of water, minus 300. Doesn't really matter. Formation of ethanol is plus 250. I'm making these numbers up. If they give us that, then what we can do is immediately we know how to build a cycle. And what now goes on the bottom of my cycle is the elements. Yeah. So what do I need to build? Everyone here. I need hydrogen, I need carbon, and I need oxygen. So the cycle becomes very straightforward. You just put all the elements needed to build these in their standard states. Yeah, so we need to go hydrogen as a gas in a pair, carbon as a solid, yeah, oxygen as a gas. And what that means is we're then going to just create everybody as the arrows always go up, like that. Yeah. So it's really easy. Then you have to balance the cycle, by the way. And remember, cycles balance in 3 directions. Yeah, each segment should have the same number in it. So on this side, we've got 2 carbons, 2 carbons down there. I've got 2 over there, that adds up. Hydrogens, I've got 6 hydrogens, so I only need 3 there, and there's 6 hydrogens over there. And then oxygens wise, we've got 1 oxygen there and 1 oxygen, so I need a half there, and I'm done. I don't like how tiny that pen is. It's ruined it for me. There we go, half there. Yeah, so now I've got a balanced cycle, and now I can just insert all my datas onto the arrows. Yeah, so formation cycles are nice, and the rule is for formation cycles, elements go on the bottom. Rule, I wanted to change to red. Nota bene. Nota bene. Yeah, formation cycle, elements on the bottom. Yeah, there we go. So what happens in a combustion? Yeah, oh, and the arrows go up. Elements on the bottom and arrows go up. Yeah, like that. That's a good way of doing it. Right, what is a combustion cycle? If you want to take a screenshot of that, guys, or pause the YouTube video, more than welcome to. Yeah, so what does a combustion cycle then look like? So let's say I'm given combustion data. The heat energy change when 1 mole of a compound is completely burnt in excess, that doesn't have to be a compound because it can be a hydrogen. 1 mole of a substance is completely burnt in excess oxygen to form CO2 and water only, all under standard states and static conditions. Let's burn somebody. Yeah, no, let's do something else. Let's stick with the same one. Yeah, let's stick with the same reaction. Ethene plus water goes to ethanol. I know it's reversible. Ethanol, there we go. Right. The equation's balanced, which is awesome. Right, I'm now going to do a combustion cycle. Yeah, combustion cycle. So combustion cycles, again, if you've got pure data. Yeah, just to show you a question, what I mean by combustion data and where they are. There, look at that. There, we've got combustion data. So I can build a combustion cycle using that. And the great thing is combustion cycles, like formations, have a lovely rule, which is on the bottom. Yeah, goes CO2 and water only. These are the things that we can make in burning. By the way, just to point out, you can, if you end up adding something, if there's something else like sulfur, you get SO2, just so you know. But just, if that's a nota bene, really, you know, in combustions, if sulfur is anywhere near anything, if it's in something, you will make SO2. It's a good rule, really. So anyway, what we can now do is we can burn everybody. I can burn ethene and turn it into CO2 and water. I can burn ethanol. I can turn it into CO2 and water. And the great thing is water to water doesn't count. You can't burn water. So it disappears from the cycle in this particular example. So you pick up a cool rule. We then, of course, need to balance it 3 ways. Yeah, balance it 3 ways. So on this side, 2 carbons. Okay, 2 carbons. On the other, on hydrogens, 6 hydrogens. 6 hydrogens. Yeah, there we go. Now, at this point, people are going to go, well, hang on a sec, because it doesn't balance for oxygen. And I'm like, I know. And that comes from understanding the equations. And I'll show you that today. We'll do that combustion cycle. We're going to do the cycle and the equations. Yeah, but the only thing you don't have to balance for, it's a nota bene. Nota bene. Oxygen. Ignore oxygen. Yeah, ignore balancing oxygen. Ignore oxygen balance. Only with the bottom one, by the way. Yeah. The reason being is it's going to cancel out in the overall equation. It's all, you'll see that. It's a weird thing. But the rules for this, let's create the rule box. Rules. Yeah. CO2 and water are on the bottom. If you have delta H combustion data, CO2 and water on bottom of cycle. I like it. And the arrows point down. That's so important. By the way, I just try to avoid point down, and I'm just gonna, yeah, that's so important. Yeah, they point down. Notice the complete opposite of formation. Formation, they go up, and combustion, they come down. I'm doing dances in my house here, and you can't see anything. I've realized I'm an idiot. Okay, so now that we've kind of looked at these cycles, we need to put them into practice. Now, since we had a combustion one, let's have a go at this particular question. Okay, so what I'm going to do, I'm going to snip this. I'm going to move it somewhere else. Okay, let's do that. Right. Is that going to just let me write on it? I don't know if it is. No, it doesn't. Edit, copy. Right. I'm going to go to, I've realized I put all these things in and then not given myself any space. Well done, Mr. Duncan. Excellent. Good job. Am I talking about myself in the first person? There we go. Right. In. I like it. Okay. So it says, use the data book values of the entropy changes of combustion given in the table below to calculate the entropy of formation of ethanol. Right. So what I'm going to do is I'm going to show you both methods. We're going to do cycle first because I have combustion data. I can create a cycle. And then I'm going to do the equation method. And what you're going to see is the heat changes are exactly the same. And you can decide what method you prefer. Okay. So first challenge of this question is I need to create that equation. So that's one of was nice why we did an exercise in the lesson. So I'm just suddenly realizing, what time does this lesson finish? Because it's Friday, I'm always out of sync a little bit. Oh, stop it, just do what I'm asking you to do. It finishes at 9:05. Okay, 10 minutes, yeah, I'll do. Okay, so I've got to create the formation of ethanol. So I need to make ethanol. Oh, yeah, I'll stick with green. CH3, it's really nice to pick this one actually, just because it's reinforcing the ethanol again. I need to make CH3, CH2, OH. Right, enthalpy of formation. Yeah, I need to make it from its elements. I need carbon as a solid. I need hydrogen as a gas. Yeah, and I need oxygen as a gas. I like it. Now I need to balance the equation. I need 2 carbons. I need 3 hydrogens. I'm going to move that little plus. And I need a half an oxygen. Yay. Right. I have got combustion data, which means step number 1. On the bottom, we'll go CO2 and H2O. God, I love it. Yeah, in their standard states. That's a gas and that's a liquid. Right. Now we need to, of course, point all of our arrows down. Burn carbon. Yeah. So notice, by the way, there's something which I haven't really described here. The equation is split into 2 parts. We've got reactants and we've got the products. And what you notice is that when you do the arrows, You know, some people like to do it with them coming straight down. You can actually do that. That's okay for you to do that. It kind of depends on what you like in terms of preference of how a cycle looks. I prefer to actually point them to the people, but as I said, it doesn't really matter. But as long as, if you're on the reactant side, you're not doing an arrow like that. Because what will happen is it'll flip over your issue in terms of whether it's with you or against you. That's why. So as I said, some people like to do vertical ones. But I'm going to burn 2 carbons and turn that into CO2. I'm going to burn 3 hydrogens and turn that into water. Yeah, that's going to go to the water. Woo, over there. Not that it needs to be pointing exactly at it. It really doesn't really matter. Yeah, and then I can burn ethanol and I can form CO2 and water as well. You can't burn oxygen. That is not a thing. Yeah, oxygen is needed to burn it. Yeah, but it's not going to appear in the cycle because you can't burn oxygen in oxygen. That's just common sense. Right, balance the equation. I'm going to need 2 CO2s. I'm going to need 3 waters, and I'm done. It all adds up on all 3 sides to boot. Isn't that nice? All 3 sides add up. Excellent. Right, now what I can do is apply all my numbers. Now, here's the number says burning graphite, burning carbon solid. Oh, there he is. And it says it gives you minus 394. Now, but the thing is, here's the clever thing. That's minus 394, but I'm burning 2 of them. So I'm going to double it. Next, I'm going to burn in the table. It says I'm going to burn hydrogen, 1 mole of hydrogen. And I get minus 286. But I'm burning 3 of them. Times it by 3. You can't burn oxygen. Move on. I am burning 1 ethanol, which means it's exactly the same value as they give me in the table. Amazing. Right. Now I do the most important arrow in all of Hess. That way equals that way. And now I create my equation. So delta H question mark, yeah, delta H question mark equals, right, is this guy with me or against me? He is with me. So plus, that says with me, yeah, with me, brackets, minus 394 times 2, close brackets. Is this one with me or against me? It's with me. So I'm going to go plus, with me, with me, brackets, minus 286 times 3. Yeah, times 3, brackets. Is it with me or against me? It's against me, minus against me. Why are the arrows pointing down if it says it's formation? Winkit, great question, thank you. Because in the question, it's asking you to work formation out, but the data, Winkit, it's all about the data, Yeah, the data decides on the cycle and the arrows. Good question, I'm glad you asked. Minus brackets, minus 1370, and I'm done. Right, I can now spit that out. I'm going to spit that directly into my calculator, exactly as I've written it, by the way, because my calculator, I'm going to literally be really slow on this. Plus brackets minus 394 times 2, close brackets, plus brackets minus 286 times 3, close brackets, minus brackets. That's the sticky button there, minus 13.7. I've typed that in exactly as I have written it down, and I get an answer of delta HR as minus 276 kilojoules per mole. Winner. Okay, now I'm going to impress you all, because now I'm going to prove that that's correct without even having to check the answer on the mark scheme, because I'm going to do it in the other way as well. Okay, so here's how this now goes down. I'm tempted to delete that other method. You guys have got it on YouTube anyway. I'm running out of time, so I'm tempted just to clear it. I'm going to clear all this. Boom. You can always rewind the video to go back to that if you want it. Right. I'm going to do this by equations now, folks. Right. So I want to do the entropy of formation of ethanol. CH3CH2OH from its elements 2 carbon solids plus 3 hydrogen gases plus half oxygen gases. Right, I want to build that equation from this data. Right, I've got to write the equations for each one. So it says combustion of carbon. Let's write the equation. Right, so carbon plus oxygen goes to CO2. Perfect. Right, I'm going to put solid, and then I'm going to put gas, and then gas. Not that I really need those, to be fair, in this particular scenario, but I'm doing it anyway. So that there is the complete combustion of carbon, and that there is minus 394. Right, but the thing is, I need to double this because I need 2 of them. So I'm going to double the whole equation, and I'm going to times that value by 2. Next, right, and by the way, notice the carbon is on the correct side of that equation. Yeah? Next, the combustion of hydrogen. What does that look like? H2 plus, suddenly realized I'm just going to move him over to there, 2 O2s, just because you're going to see something really cool happen in a second. So hydrogen gas, I'm just trying to put them under the right places. Hydrogen gas plus oxygen gas goes to water. Yeah, it goes to water. Right, that's the combustion of hydrogen, but now I need to burn 1 mole of it. I need to balance the equations. Yeah, so that would be that. That there is minus, I'm going to put that underneath it, minus 286. Yeah, the combustion of 1 mole of hydrogen. But how many am I actually burning? I need to burn 3 of them. So I'm going to multiply this equation by 3. So that becomes 3 there. That becomes 1.5 here. Ugh. 1.5 O2s there, and 3 waters there. Next, right, oh, hang on, so I need to times that value there by 3 because I need 3 of those equations that I had originally. Right, now I'm going to burn ethanol. Right, so I'm going to take ethanol, CH3, CH2OH. I'm going to move that. Sorry, CH3, I'm running out of time. CH2OH plus O2 goes to CO2 and water. Now, here's the cool bit. The problem is, if you notice, the equation I am trying to build has ethanol on the other side. By the way, I'm going to balance it before I forget. So 2 carbons there and 3 waters there and 3 oxygens there. But what you notice is I'm trying to build this equation from these equations. And at the moment, I've got my 2 carbons. I've got my 3 hydrogens. What I don't have is my ethanol, and my ethanol is on the wrong side. So what I'm going to do is flip the equation over. I'm just simply going to reverse it. Right, trying to reverse that in my head because I've run out of space, haven't I? Because I'm an idiot. Let's get rid of all this. Yeah. Yeah. Okay. So I'm going to flip that equation over. I'm going to make the ethanol on that side in the position underneath what I want, plus oxygen, and that's being made from carbon dioxide and water, and then I have to balance it, 2 carbon dioxides, 3 waters, and then how many oxygens? 3. Right, I've reversed it. Now what that means is, in terms of my data, it means that that value must be flipped. The sign must be flipped. So that's now going to be plus 1370 inner brackets. Yeah, I've just reversed the whole equation. I've flipped it over. If I flip it over, I flip the enthalpy sign because it's the opposite. Yeah, right. And what do you notice? This is the amazing thing. Why do you not need to balance a Hess cycle in a combustion for oxygen? The reason being is, look at what happens, guys. Carbon dioxides cancel out. The hydrogen, the waters cancel out. 3 waters on that side, 3 waters on. What happens to the oxygens? Oh, look, I've got 2, 3.5 on that side, and I've got 3 on this side. All of those disappear, and I have all of those are gone, and I've only got half an oxygen left. And look, it gives me the perfect equation that I wanted. Everything else disappears. It's beautiful, beautiful chemistry. Right, all we have to now do is add all 3 of those together. So we just say delta H equals, delta HR, I'll just go for action, equals, I'm just literally going to add them all together, plus brackets minus 394 times 2. Yeah, plus brackets minus 286 times 3, plus brackets plus 1370. And if I just literally type that into my calculator in that line, plus brackets minus 394 times 2, close brackets, plus brackets minus 286 times 3, close brackets, plus 1370, close brackets. And I get exactly the same answer as that. If I type that into my calculator in one big long line, yeah, I'm just going to do that just because I think it's important to actually show how I've typed it in on my exact calculator exactly. Plus brackets, plus 1370. I just add them all together. And it gives me exactly the same answer, 276 kilojoules per mole. I know I'm right. Both methods, cycle method and equation method. Now at this point, I think people, oh, that's so cool, piece of art. Oh, thanks guys. It is amazing, isn't it? That method there gives me goosebumps because it all disappears and you get the equation you're building. It's such beautiful chemistry. Love it. Right, guys, I know it's the end of the lesson today. So what I'm going to ask you to do, I'm going to ask you to leave the YouTube video. You can go to your next class. However, I'm actually going to continue the YouTube lesson. I'm just going to do one more example, and then you can come back to this when you've got a bit of free time. So let's go back to my questions. I just want to really hit this home because I love this. It's beautiful. It's such lovely chemistry. I just want to show you another one. Right. Okay. So this question, really, really difficult. And do you know what? That's actually not a good choice for me because for me to build that cycle is going to be horrible. What I'm going to do is that one's going to be a very big set of equations. So let's have a look at this particular question. And I'm really tempted then, I'm going to snip that. They're pushing us into a cycle. So obviously we have to use it. Oh, darn you. No. Yep. Oh, I've cut the top off. Let's try that again. No. One more time. No. Come on. Come on, Mr. Tablet. I've caught the top. That's just fine. Right. Edit. Copy. Let's go then to quick notes and go next question. I like it. Right. So I'm just going to, again, this is a combustion cycle. Oh, I don't want a combustion. Change my mind. I want a formation. That makes a lot more sense for me to choose if I have one on the hand. I do. I do have one. Oh, yeah. This is awesome. Okay, guys, love this. Let's go for this one. This one's much nicer because there are loads of other little snippet questions here which are worthwhile me showing you as well. Oh, this is great because this one's going to be a beautiful example of how you can use both. And I'll really enjoy this one. So, quick note. Okay. Oh, hang on a sec. Uh-oh. Suddenly realized something. Guys, give me just 2 seconds, please, folks. Okay, hang on 1 second. Hang on. Sorry about this, guys. I'm just sending. Okay. Hang on 1 second. Oh, it's not a good idea, this, is it? Okay, right. I've got 5 minutes. Let's go. I love this example. I'm going to do it super quick. So first things first, it's formation data. I don't even bother about the rest of the question. I don't care. Yeah, all I care about is the data. So my arrows go up, and on the bottom goes, I'm tempted to remove, no, I'll just keep going. So, okay, on the bottom, elements, Sb, antinomy, plus carbon, plus oxygen. Anything else? Nope, that seems to be all of them. Cool, there's my bottom part. I need to balance it. How many carbons do I have? I've got 3. How many oxygens do I have? I've got 4, so I need 2 of those. How many antinomies do I have? I've got 2. Cool, okay, so with formation, arrows always go up. Boom, 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 boom. Oh, no, notice something. One of the arrows disappears because we're going from 2 antinomies to 2 antinomies. Well, that doesn't matter, does it? Although it is rather odd, it is not in its standard state. Antinomy, oh, isn't that fascinating? Guys, we have to We do have to include that one. That's a nightmare. Oh, what a faff. We do have to include it in the equation because it's standard state for antimony. It's a metal. It's a solid. So we are going to a liquid. So we do need to include that. What a nightmare. That's the A-level bit there. Tough. So this says formation of antimony from its things is minus 705. There's a 1 there, so it's times by 1. I'm going to make 3 COs. There's CO, there's its value, so minus 111 times by 3 because I'm making 3 of them. 2 antinomies to liquids, I'm starting from solid, that's plus 20 times by 2. Make 3 CO2s, gives me minus 394 times by 3. Okay, right, let's just go. The most important arrow in the whole of the Hess cycle, yeah, this way is equal to this way. Right, so we can now go delta H question mark equals, this one here is against me, minus, it's against, brackets, minus 705 times 1. Right, this one is against me, minus, brackets, minus 111 times 3. Yeah, this one is with me, plus, brackets, plus 20 times 2. That one is with me, plus, brackets, minus 394 times 3. And I'm done. Run it through my calculator, and I'm finished. Minus, brackets, minus 705, close brackets, minus 111 times 3, close brackets, plus brackets, plus 20 times 2, checking everything on my calculator because my calculator is sticky, minus 394 times 3. The overall heat change is minus 104 kilojoules per mole. Right, equations, formations. Okay, so I now need to do this via the equation method. I need to build everybody in this. So I need to build him from his elements, formation. So it gives us that, so it's going to be, but the problem is if the formation, the SB2O3 is going to be on the wrong side. So I need to, okay, I'll write it down. S2SBs plus O2s, and I'm going to need 1.5 of them. Yeah, and that would be minus 705. But what you notice is it's on the wrong side. I need it on the other side. So I'm going to flip that equation over. Yeah, and then flip the power sign. So SB2O3 is from 2 SBs, solids, plus 1.5 O2s, gases. Right, flip that, so plus 705. I have him in that equation. Now I need carbon monoxide. Make formation of carbon monoxide. It's on the wrong side. I'm making it from carbon and oxygen. I need to flip it over. So now I need carbon monoxide on that side. That means it's not the form. I just need to flip the sign from carbon and oxygen. Yeah, and it's a half oxygen for carbon monoxide. Yeah, so, and I need 3 of that there. I need to flip the sign, so that becomes plus 111. Yeah, but I need to times that by 3 because I need 3 of them in the equation. Yeah, and so I'm going to get 3 of those, and then 1.5 oxygens, 1.5 O2s. Yeah, next, I need antimony on that side. Well, I've got the formation of antimony liquid. That's exactly what I need. Antimony liquid being made from antimony solid. Yeah, and I need 2 of them. So that's going to be plus 20. It's on the correct direction. I'm going to double it because I need 2 of them, times by 2. Yeah, the next thing is I need to make carbon monoxide. Yeah, sorry, carbon dioxide. To make carbon dioxide, I'm going to make CO2 from carbon and oxygen. Right, that's minus 394. But how many do I need? I need to make 3 of them. So I'm going to triple that equation. They're all on the correct side. I'm going to times that value by 3. So I don't need to reverse it because it's on the correct side. Right. So now check the beautiful part of chemistry and how everything disappears. Right, so I've got him here, right? I've got, so hang on a minute. Just make the people disappear. So I've got antimony solid on opposite sides. I've got, I've got carbons, 3 carbons on opposite sides, make them disappear. Next, I've got oxygens. I've got 3 oxygens there and 1.5, 3 oxygens over there. They all disappear, cancel out. Amazing. And what do I have left? The exact equation that I wanted. So now I just add all of those together in one big long line. Add, type it into my calculator, plus brackets, plus 705, close brackets, 705, close brackets, plus 111 times 3, close brackets, plus bracket, plus 20 times 2, close brackets, plus brackets, minus 394 times 3, close brackets. And the answer is minus 104, which is exactly the same answer that I had for the other. Guys, I'm going to leave you be at that point. I've overrun my lesson by a minute. Can we get told off? Guys, have a nice rest of your day, and I will see you all soon. I hope that was useful. More questions to come. I'll see you all soon.